So the law of conservation of mass says that the mass of the products will always equal the mass of the reactants. So if I'm performing some kind of chemical reaction, let's say I'm going to burn methane. Okay, when I did the demonstration where I lit my hands on fire, you know, with the bubbles, I was burning methane. So methane is CH4, it's a gas, and I burn it by reacting it with oxygen, which is also a gas.
Is that supposed to be an S?
This right here,
Yeah.
that's a G. Okay? So, and then when I burn those, I get carbon dioxide, which is a gas, and I get water. And water, when I have a heat like I had when I was burning it, you get water as a gas. Okay? Yes, they're all G's. In the parentheses, they're all G's. Okay? Yeah, I'll hold for 1 second. Sure. There's too much complaining in here.
Yes,
Oh, that's just mean. We don't want to do that. We want him to be here. We want to just transform him into a full cavalier.
I remember doing this.
I may don't remember what it is.
Really?
Somebody put the dog outside.
Why are you laughing? It's not funny.
That sounds like wet dog.
That is so mean.
She's sorry.
I hope y'all know I go home and cry. Is that reaction?
Now, do you wipe your tears with your hind leg?
Oh, well, let's not even go there, okay?
That's CH4.
CH4
Plus what?
O2 Everybody got that? Has everybody got this? Anybody still writing this? Okay. In order for the mass of the reactants to equal the mass of the products, we have to have the same number of atoms on both sides. Okay? Do we have the same number of atoms on both sides?
That's like when you have to add the substance.
How do you get the atoms to be the same on both sides? What do we got to do?
You gotta do the even amount.
Plus 2.
I forgot
I mean, yeah, times 2. 2 in front of CO2.
2 in front of CO2?
No, 2 in front of O2.
2 in front of O2?
No. Wait, what do we do? What's the answer?
We're trying to get the number of atoms to be the same on both sides.
Even on both sides.
Right?
It kinda is, but you so. Oh, I know what you have to do.
You gotta put a 2 in front of H2O.
I know what you have to do.
2 here?
Yeah.
All right, I'm going to put a 2 here. Is that going to fix it?
Yes.
Yes. Let's make sure. No, it doesn't. Yes, it does. No, it doesn't. No, you have to put a 4. No. No, you don't. It's good. It's good. It's good.
No, it's not good.
Put the 2 right there. The 2 that makes the H a 4 and the O. You need to put a 2 in front of the CO2.
Really?
And erase it. Yeah, because. No, you don't.
Yeah. Put, and then put a 2 on the other side.
Where?
From the CH. Right?
No.
Okay, erase everything. All right, guys. Now let me show you something. We're gonna do this later in the semester, but for just right now, I'm gonna give you an introduction to something called an atom inventory. Because the reason you're having trouble with this is it's kind of hard to keep up with all those numbers, isn't it? Would you say so?
Yeah.
All right. So an atom inventory simply takes and y'all remember what an inventory is? Count everything. So I'm going to list everything. Like I'm going to list carbon, the C here. I'm going to list hydrogen, the H, and O, the oxygen. Shh. And I'm going to make a kind of little bitty spreadsheet. Okay? All right, what I want to do is count all the carbons on this side. How many carbons do I have right now? One carbon. How many hydrogens on the left?
4.
Oxygens.
2.
Over on this side, how many carbons do I have?
1.
How many hydrogens do I have?
2.
How many oxygens?
3.
3. Do you see 3 of them, guys?
Yes.
2 here and 1 there? So what we're going to do is, as we try to figure out how to balance it, we're going to go back. We're going to keep changing this until everything works out. Okay? So I've got, right now I can see I've got 4 hydrogens on this side and 2 on this side. Now Rose was correct, I need a 2 here because I'm going to have 4 hydrogens, right?
But that don't make it 4.
It doesn't make everything work out, that's right. But let's recount everything now, okay? Alright, so now that I've got 2 waters, that makes 4 hydrogens. 2 times 2 hydrogens is 4. But it gives me 2 oxygens here, and I've also got those 2 oxygens right here. So now I go back over here to what? Okay, so I put a 2 in front of the O2, and that will give me 4, and everything is balanced out. Would you find that a lot easier to balance equations? Yeah. All right. So that's what we're going to do. Now that we have the same number of atoms, then both sides are equal. Okay? Both sides are equal. So if I put the mass of this on a balance and the mass of this on a balance, I should get them the way they should weigh the same, right? You think? They're gases. What happens if you put a gas on one of our balances back there? Does it weigh anything?
No.
It's because of something called buoyancy. Now it would work if you put it on a balance and put the balance in a vacuum. All right? But we have that, so you got to be careful. All right? Sometimes when you're trying to weigh things, you don't get what you think you're supposed to weigh. That goes back to understanding what's going on down here at the atomic or molecular level. So you got to use your imagination and do this focused sort of daydreaming where you're thinking about what's really going on. That's modeling. All right? Modeling is how scientists figure out how things work, right? And chemistry modeling, it means we're looking at what's happening with those atoms and molecules and ions. Okay? All right. But if everything's worked out, then the mass of this side and the mass of this side will be equal. So a lot of times we think about matter as being something that has weight, but it doesn't. It has mass. And mass doesn't depend on gravity. Weight does. How much do you weigh on the moon? Less than that. 1/6 of what you weigh here. Okay? Shh. All right? But now your mass is the same. You didn't change your mass. You just weighed yourself on the moon where the gravity's lower. Mass doesn't depend on what gravity. Okay? Weight does. So when we say mass, we mean that actually the momentum of these particles is the same. The total momentum of all these particles will be the same. That make sense? Okay. So mass doesn't change from products to reactants or reactants to products in the law of conservation of mass. But as we,
I was about to go back to the little periodic table. So does that mean that basically all the gases on the periodic table? Am I going somewhere with this? Is there gases on the periodic table?
yeah, well, there are elements that are typically gases. Yes.
Does that mean they weigh less?
They would weigh less.
But their mass would be.
Well, that really doesn't fully flesh out the whole story, but you're essentially correct. Okay? Yeah. All right. So we can put both of these on some kind of a double beam balance here.
What is that? It's still.
It's a double beam balance I'm putting it on. All right. So they weigh the same. Okay? Just kind of a cartoon version of a double beam balance. Okay? All right. So the reason that the mass is the same is because the matter didn't change. The actual amount of matter doesn't change. So we could also state the law of conservation of mass as the law of conservation of matter. Okay, so I want to stop the recording here for a second.